Title is Hot Atomic Scale Dipoles and Cool Ferroelastic Domains Stabilize the Ferroelectric Polarization.
Thank you, Chair. Thank you today. And I would like to thank also the organizer for inviting me over. And plugging the computer. All right. Okay. Just a second. Yeah. Hi. So I'm going to discuss today about the collectiveness in ferroelectricity. What you see here are, this is a picture that I took in Stockholm of two bears that were just awake after hibernating for the entire winter. And these two buddies are really excited about having some interaction together. And on the other side, you saw another video that I took in Eilat, in the Red Sea, in Israel. And you see this school of fish that works collectively. Still, they can have some kind of excitations. You see these bigger fish try to approach and to eat them. So in this topic today, I'm going to try to understand, or in my group activity in general, when the bears become fish. So the origin of this kind of collective behavior. So this is what I hope to discuss today. So with respect to ferroelectricity, of course, we are talking about at the atomic scale, we have the dipole moments, and maybe we have some kind of intermediate structures of local order, and then we have the polarization that can be macroscopically. So that interface between the two, this is what I would like to emphasize today. And as you saw, I like to discuss with pictures. So the way we took our pictures is to take the atomic scale, we use the TEM usually, different methods, and with the AFM, we do different methods of the polarization. So the origin of the ferroelectricity, of the collective behavior of the dipoles is, of course, at the ferroelectric transition or transitions, either from the paraelectric to ferroelectric phase or between one ferroelectric to another ferroelectric phase. So this specific example is, of course, from the seminal material of barium titanate, and almost all of the discussion today will be about single crystal barium titanate, about this specific seminal material that has been researched for a while. So, of course, ferroelectricity is not alone. When we bear in mind the perovskite materials, so we have to consider also the ferroelastic interactions. So these are the early works. Yesterday we had a very nice introduction. Some of this literature was mentioned also by Irka, who gave that introduction. And when we talk about what the mechanisms of what the structures, so you know that since about the 90s, Roitward gave very nice explanations about the organizations and formation of domains in polytwins, and maybe Pompey also emphasized the relationship, the interplay between ferroelasticity and ferroelectricity. And so this is one approach, that when the strain makes a very organized and ordered structure. And another approach that can be maybe emphasized also by the review from Echal Tzalieh, both of them are in the following speakers. So here you have a lot of emphasis to the local effects, actually, to pinning and unpinning. And this is exactly the balance that we wanted to see at the phase transition. So, of course, this is a non-exhaustive list of the literature, but this is just representing what I would like to say. So one example is at the nanoscale. So what you can see here, these are the... let me try to use the pointer. Does it work? All right. No. Okay, which one? Thanks. All right. So what you can see there, this stripe. Okay, we're talking about this. This is not barium titanate. This is the only material that of mine that you will not barium titanate. And you will see a polycrystalline materials, and all of these stripes are kind of ferroelastic domains. And when we look in here, you see that there is a split, which means that you have a local kind of twinning kind of defect. It can be either a needle domain or a different kind of defect, what you have in here. So in order to see the influence of this specific defect on the ferroelectric domains, we applied a voltage here and switched the polarization. And as a result, you see that you can get indentation. So this is indented here, and it's not a perfect circle as you would expect to have from this specific tip. So we can quantify that. We quantify the energy that you can get out of a single pinning site. So it means that single pinning sites can, or such ferroelastic domains, okay, or can change, can affect, as we know, the ferroelectricity. And we know also that when it's organized, of course, it can make also a different kind of organization of these effects. So this is another coupling. And this indeed has been observed in the literature. So you see that it's, when you talk about the polytwins, they're not always infinitely coherent, but sometimes you have structures that go like that, and then another structure that go another direction. And this has been shown in the literature, and we emphasized it some time ago to show that there is, so we call them kind of bundles of this kind of ferroelastic domains, and we show that the importance to the macroscopic ferroelectric domains. So you see that the polarization to transfer between in and out, it has to go through a perpendicular ferroelastic domains. So, of course, both domains are important, and we want to emphasize again the phase transition at the ferroelectric and ferroelastic transition, and therefore we cannot bear in mind only the electrical part, the polarization, but we have to bear in mind also the elastic part. So, as Jim Scott mentioned yesterday, we recently looked at the work by Wang and Zhao from MIT when they looked at soft matter on the ferroelastic domains, and they show that you can have different effects such as wrinkling and creases and other structures, stable structures, and they formed a stability map which may be universal. And maybe they can be applied also for ferroelectricity and ferroelasticity, and I just want us to bear that in mind. So if we talk about the phase transition, what do we expect to see? So maybe one of the first papers regarding that is by Cochrane, who talks about the frequency that goes to zero. And of course, later we had the paper by Cohen, who discusses the short-range interactions versus long-range, which means the defects versus carriers that screen the field, and this kind of interplay. And indeed, later we had some experimental results from X-ray and from NMR, and then maybe understanding of the two. And in the end of the day, today we have maybe sometimes we think that there is some kind of a mixture between displacive and order disorder, or let's call it now diffusive, in some cases interaction or interplay in the phase transition. So this is specifically what I'm trying to see. The nature of that, the origin of the nanodomains, the atoms, how they organize in the displacive or the diffusive part at the phase transition. So in Yiddish, it's called the pitchivkes, and these are the dots of I and tags of T that are making the phase transition. And this is what I'm looking at. So I'm not the first to see to look at that in this respect. So Elisabeth Zoregel from Germany, so she cooled down from 20 Celsius to minus 20 Celsius barium titanate, and you see that here it's purely tetragonal, and here it's purely orthorhombic, and she analyzed very, very nicely the orthorhombic domains. And she saw that you can have this transition, and she can observe that. But I'm interested to see the transition itself, and therefore we have to see the dynamics. And so here it's you change temperature. You take a very slow scan. These are rastering. It's AFM, and then you change it from plus 20 degrees to minus 20 degrees while you scan in the AFM. So what we did, which means my students, Asaf Ershkovitz, Alon, Hendler Avidor, and Florian John, who is from Asylum company, the AFM company, we collaborated to have this kind of phase transition experiment to look at the orthorhombic structures and then to let them to see the dynamics of the domains. So I'm going to show you a movie, and I'm going there to show you the different steps one by one. So you will see soon the tetragonal phase entering here. You see here the temperature. Okay, oh, it went very fast. And now you see the tetragonal stripes, and some of them will close. All right, it's expedited. You see, you have some kind of coarsening of these stripes, and Alon came up with the name of zipping, and then you have some kind of relaxation here. So we saw that several effects take place in the phase transition. So let's take a look into them one by one. So the first, we start with the orthorhombic phase, and we end up with the tetragonal phase. And in between, this is kind of the typical structure. So what happens, you will see when I complete this figure, this slide, that you will see that we have kind of wavefront. They're going from up to down. This is what we see. And you see that it's asymmetric. The C domain, in this case, is the darker areas. They go faster than the A domains. As a result, you may have some kind of effects, such as shear. And then when the shear exceeds a certain value, we can see leftovers of pinning sites. So this is what we see in here. This wavefront that goes down, you see, in this direction. And after it crossed, let's say, you see that there is a gradient here, then you start getting this kind of islands, pinned islands, and the transition is complete, and you still have these areas. If we take into account Elizabeth Zoregel's analysis, we believe that these are orthorhombic leftovers, but we cannot be sure. Anyways, these are different domains. So I showed you only one type of the PFM image, but of course you can look at the topography, and you could look at the D33 and the D31 to get the 3D structure of the entire domains. So after we saw the wavefront, what happens in the phase transition, again, we discussed this kind of leftovers as a result of the shear. You see that the C domains go faster than the A domains. So we're not sure about yet why it goes like that, but Maya, who does some crystallographic analysis of that, are getting there, but we are not yet sure why we get this difference between the speed, the rate of progress in C domain versus A domains. The next thing is actually chronologically was earlier, is the pre-transition. If we look carefully at the topography image, you may see here a stripe. This is in the middle of the transition. So I'm going to show you that you can have this stripe moving, and it plays a role in the transition itself. So let's take a look what I mean by that. So what you see here, this is the same video that you saw before, but just of the transition. And here you can see this kind of lines in the topography. You see one fine here, and then two here, and then another two here. So it goes in kind of periodic structure. And you see as the phase coming in, so you lose them one by one. And when you lose them, it's not where the transition, when the front of the transition, it just kind of being pushed away. So this is what we see in here. So this is the pre-transition actually process. So this is how it looks like when we look samples of these images. So you see this one, and then when the transition arrives here, you lose one of them, and etc. until everything is gone. So this is maybe if we bear in mind the analysis that we discussed about the soft matter, the analogy, so then it means maybe we have some kind like ripples. After some discussions with Jim, this what was suggested. And indeed, I looked into it a little bit more in detail, and I saw that maybe type of ripples, maybe it's reminiscence of what you have in what's called in bed forms. So these kind of ripples that are straight lines, you can have them in the sand. And they also have some kind of stability maps that as a result of shear, exactly like we have in our ferroelastic domains, and what we expect to have in the phase transition, in the share. So they are not only there. This is a picture that I took from the airplane above Nebraska. These are clouds. They behave similar to that. And another interesting example is if you look at a tooth rock, from volcano, you can see the bed forms and how they influence the layers in here. So in Israel, we have the Golan Heights. I went there with my family. This is my daughter modeling. She didn't know at that time. I didn't know as well. Not very far from where the unfortunate battles in Syria go. But you can see here that the layers go and have some impact due to this kind of thing. And this is a museum, a volcanic park. And when I looked at later at the explanations, I saw that this is like a droplet of lava that make an impact here. And as a result, it pushed the other layers, maybe similar to what we see in our phase transition. So we discussed what happened during the phase transition, but then it's not over yet, because as you remember, we have some kind of coarsening or zipping, what we said, about that you see here, an area with pin domain, an area in here, it makes some stress, so the stripes tend to be wider. And let's see here, in this movie, we see these kind of events, several of them. What you see here is the progression of the zipping as a function of time. And if you look at the rate, for those we saw, they are kind of linear with respect to what we see. We saw the first one was very fast, the second one was slower, and then gradually even slower. So this is a slow process, or actually the range changes. And then if we bear in mind what it should be, maybe we expected to have some creep, but it still can be, because if you remember, the creep is about the exponent about unity, one unity, and we have some kind of distribution. So it's not contradicting to that, but anyways, we see that each of these events is nearly linear. This is what it behaves. So we talked about what happens again during the wavefront that goes and makes the phase transition, but then we have this kind of leftovers, and we want to get rid of this, to relax. I mean, the barium titanate want to relax, and therefore to let this kind of, if these are orthorhombic domains, so, because this is a first order phase transition, so again, it has to disappear with time, and this is what we see in here. So this is, of course, much faster than it was before. And you can see that the rate changes with time. But anyways, you see some kind of relaxation. The topper is going slower. This one is going faster. And then we stopped our experiment after about 20 hours, after cooling and heating the temperature for only a few degrees. All right. So this is, as I said, we discussed about the ferroelastic domains, but I was kind of deceiving because I told you that we want to see also some other effects of the polarization. So I'm going just briefly to say that, all right, before I will, sorry. So we saw that, let's conclude what we had with the phase transition. So in the beginning, we have the pre-transition, the ripples that we saw, maybe this direction, and this is displacive because you see that it's organized together. Then we saw this wavefront that going together. So this suggested